Good evening, calculus students. Welcome to our first e-learning day. I know it's a little odd for me to have an e-learning day with you guys because I haven't seen some of you in like a week due to my kids getting sick, my husband's sick, and then they got me sick. So I'm going to just try to kind of figure out where everybody was at, make sure that we're all kind of on the same page, and go from there. I might separate this into two different videos if it's going to get a little long, so it's just easier to upload. But hopefully you can follow along. Feel free to pause it whenever you need to, mute it whenever you want to not listen to me. You don't get to do that normally. If my dog starts barking and my kids start crying, well, you'll get the glimpse into my real life. All right, so what we're going to start talking about today is, not start talking about, you guys already did it last week when I wasn't there, are the separable differential equations. Now, we're going to get into solving some of these equations, but there's going to be some things that we're going to do in them that I need to have you guys have some context behind. So that's going to require me to backtrack a little to talk about some things that you did in Algebra 2. In Algebra 2, one of the big topics was the exponential functions and a lot of the applications to them. Now, you have seen these exponential functions, and they're typically of the form a equals pe to the rt. Some of you guys might have seen them differently with and not e to the rt. So there's a variety of different variables that can be used, but the basic thing here is that you need to know that your e is your natural base, and it is the base of your function. Now, this is what you guys saw when we were just looking at these as functions. But when we have something that is going to be representing exponential growth, or decay if the constant is negative, we also have a differential equation that we can use to represent these problems. Now, what we're going to do first is we're going to go through this, and we are going to actually solve this differential equation. Now, when I take a look at this, I can see that I have a y here and one here. And then these don't match, but that's fine. So what I'm going to end up going to do is I'm going to rearrange this so that I have 1 over y dy equals k dt. And so now that I have that, I'm going to find the antiderivative of each side. And so we know that this is going to be the natural log of the absolute value of y equals, and k is a constant, so this is going to become kt, like me, plus c. Now, at this point, what we're going to do is we're going to try to solve for y. Now, in order for us to do that, we're going to change this so that it's an exponential form. So that means then that I'm going to have the absolute value of y equals e, because that was my base of my natural log, to the kt plus c. Now, from here then, I know that y would equal plus or minus e to the kt plus c based on what we know about absolute values. And so if I rewrote this now so that I had y equals plus or minus, I could rewrite this as e to the c times e to the kt. Now, when I go ahead and I do that, the reason that we're going to do this is because this e to the c, well, remember, whenever we've been solving these differential equations, this c is representing a constant. Well, so e to the c, that is a constant. So we're just going to call it something different. So I could say, let's call it, let's go with, I don't know, e plus, we'll do the plus or minus e, we'll call it a this time around. And so when I go ahead and I do this now, what I'm left with, and I'm left with y equals a e to the kt. Now, it's different variables, but if you can tell, you've seen this before. So when we're taking a look at this equation here, this is representing an exponential growth equation. It's just the differential form of it. And so you're gonna see us working a lot with this e to the c, and we can do it a few different ways when we're going through and dealing with our problems. So I wanna take a look at another example here with you all. Ooh, my friend fell. Okay, so it says that we are going to look at this differential equation and we are going to solve the initial value problem. So we're looking to solve dy dx equals 2 over root y when y of 0 equals 9. So the first thing that I'm going to do when I do this is obviously, again, y. I can see they're on different sides. Got x's, the x, so I'm separating this. So when I go ahead and I separate this, I end up with the square root of y dy equals 2 dx. Well, this is one of those that we've probably done a billion times, but we end up with y to the 1/2 dy. And then when we go to find the antiderivative of each side, we end up with y. If I add 1 to that, we end up with 3/2. We can divide it by 3/2, which is the same thing as multiplying by 2/3. And then we end up with 2x plus c. Now, when I'm solving a differential equation, my goal is going to be to get y by itself. So I still have to get y alone, and I still have to deal with the fact that I have this initial condition here to find my c. Now, I can really plug that in anytime I feel that it would be appropriate. I'm going to go ahead and I'm going to just multiply both these by the 3/2, and those end up canceling. And so now my equation is y to the 3/2 equals 3x plus c. Now, we're going to go ahead and we're going to solve for c. And so when I go ahead and I do this, I'm going to take my x equals 0 and my y equals 9. So now I have 9 to the 3/2 equals 3 times 0 plus c. So I end up with 3 cubed equals c. So c is 27. So if c is 27 now, my equation, I left it off over here, is this. Now, I still got y by itself, which isn't a problem, because I can just go ahead and raise each side to the reciprocal powers, which would be 2/3 in this case. So y equals 3x plus 27 raised to the 2/3 would be my final answer. Now, I'm going to give you guys 2 more examples. I'm going to stop the video now, though, so it's easier to upload. So I'll just do a separable differential equations video number 2.